Yes, so is my screen clear to everyone? Is my screen visible?
No, ma'am.
Able to hear me? It
Yes,
is
ma'am.
not visible. Now, now, now is it visible?
Yes, ma'am. Visible.
Okay, fine, thank you. So in today's class, we are going to discuss the questions on GOC and hydrocarbons. Okay. So yes. So before entering into the question, like the stereochemistry of the substitution reaction, right? So whether the reaction product will be have the inversion configuration or the configuration will be remain same. It will remain same. Okay. So for when I talk about the substitution reaction, and you all know that there are like SN1 and SN2, unimolecular reaction and bimolecular reaction. Okay. So in unimolecular reaction, okay, in unimolecular reaction, will the configuration will retain or the inversion of configuration takes place in SN1 reaction? What would be the stereochemistry? What would be the stereochemistry for SN1 reaction? So we know that like SN1 is a unimolecular substitution reaction. Yes, it is a unimolecular substitution reaction. So here in the first step, like that is in the slow step, only the substrate will involve. So there will be formation of, can I say like a carbocation will be formed in the first step. And in the second step will be the attack of nucleophile. Attack of nucleophile. So here, since it is taking place in two steps, the configuration will be like retention of configuration. Retention of configuration. But what happens in SN2, like both the leaving group as well as the attacking, it takes place simultaneously in the same step, okay? So if there is like one nucleophile attached over here, the second nucleophile will come and attack. So therefore, the first nucleophile will move out. So here you can see that this area is blocked, okay, in the front. So the nucleophile is coming and attacking at the back side. So therefore, what happens to the configuration? Inversion of configuration takes place. Inversion of configuration takes place. Okay. So clear with this thing. So in SN1, retention of configuration, that is the configuration will remain same. Okay. In SN2, what happens? The inversion of configuration takes place. What is meant by like inversion of configuration? The inversion, the rotation, configuration will just get inverted. Okay. So this is for S1 and S2. So clear with this, everyone? Clear with this? Shall we move to the question part?
मैम आपकी वॉइस ब्रेक हो रही है.
So moving to the question. Uh, is my voice breaking?
Yes, ma'am.
So everyone is it breaking or is it good? And is my voice clear to you? Is my voice clear or it is breaking? Fine. Okay, if it breaks, you just tell me. Okay, fine. So now moving to the question part. Okay. So look over Is my voice clear now?
नो मैम अभी भी हो रही है.
It's breaking again. Is my voice clear now? Pooja, please respond. Like Ankush, Pooja.
यस मैम अब ठीक है थोड़ी.
Okay, fine. Okay, so first we'll write the compound. Okay, so the what is the compound given over here is like minus 1 bromo 2 ethyl pentane, which is a single enantiomer. When on reaction with NaOH, which is an SN2 reaction, you have to match it. Okay, so first we'll write the compound. It is like 2 ethyl pentane, 1 bromo 2 ethyl pentane. Okay, so I'll just write over here like you'll be having 5 carbon atoms. 1, 2, 3, 4, 5. Okay. And you have like bromine in the first carbon and ethyl group in the second carbon. And here you can see that there is, it is like H. Okay. Ethyl group. This is what present over here. Okay. So now we are moving to the SN2 reaction. So in SN2 reaction, what happens? What would be the product in presence of aqueous NaOH? So here Br will be replaced with OH. Br will be replaced with OH. So your product will be, this will be your product. Okay, so now what happens to the configuration? What I have told you, like in SN2 reaction, inversion of configuration will take place. But look over the carbon. Look over the carbon where this bromine or OH is attached. Whether. Okay, so whether this carbon is chiral carbon or achiral carbon. What is the nature of the carbon? Whether it is like chiral carbon or achiral carbon. What is the nature of the carbon? Whether it is a symmetric carbon or asymmetric carbon. See how many hydrogen you have? Like in this carbon, you have like 2 hydrogen. Yes, you have 2 hydrogen. So therefore, we know that a chiral carbon is where all the 4 atoms attached should be different. But here it is similar. Okay, so therefore, it is an achiral carbon. So whether the stereochemistry applies for this achiral carbon? No. Okay, whenever it is like chiral carbon, this inversion will take place. But here, since the carbon is an achiral carbon, the inversion will not take place. So what about the configuration? The configuration will be the retention of configuration. That is, the configuration is going to remain same. Okay. So for the first one, the correct option is going to be like, okay. Now moving to 2-bromopentane. Now you're going to answer for this question. 2, 3, 4, 5. 2-bromopentane. So when you write 2-bromopentane, again you're going to do, you have a Br group over here. Okay, again you're going to carry out the SN2 reaction. Now can you tell me like what happens to the configuration? What would be the configuration? Whether the configuration is going to be like an inversion configuration or a retention configuration. It is an SN2. Look over the carbon. This carbon is a chiral carbon or a chiral carbon. This carbon is chiral carbon or a chiral carbon. So you have like one CH3 attached, Br over here, and you have a carbon chain attached, and you have hydrogen. So whether this carbon is chiral carbon or achiral carbon. You all know, right, what is chiral carbon and what is a chiral carbon? Yes? Okay, so put it in the chat box. Put it on the chat box. Whether the carbon is chiral or a chiral. What is chiral carbon? Where the all the groups which is attached to carbon are different, then it is chiral carbon. So here you can see that all the groups attached are different. So therefore it is a chiral carbon. So it is a chiral carbon where the substitution takes place. And this one has undergone the SN2 reaction. So if it undergoes SN2 reaction, right, what would be the configuration, whether retention takes place or inversion takes place? What would be the configuration, retention or inversion? The nucleophilic substitution takes place on the chiral carbon. So what we have studied over here, SN2 reaction will undergo inversion of configuration, okay? And in the first case, since this carbon is a chiral, we have written it as like retention of configuration. But in the second question, this is chiral. So what would be the configuration? Whether it will be like retention or inversion? Very good. Inversion of configuration. So this one would be like inversion of configuration. So the configuration will get inverted. Okay. So how will you write the product? Like if this is present in front and is it present, this hydrogen is present at the back. Now what would be your product? The product would be. So now you will be writing the hydrogen using the wedge bond and OH using the dash bond. Okay, so here you can see that Br is bonded using a wedge bond, but due to the inversion, OH is having the dash bond. Okay, so this would be a problem. Now moving to the third question. 3-bromo 3-methyl hexane aqueous NaOH when it undergoes an SN1 reaction. Okay, so already we have matched like these two. The remaining three you have to consider. 3-bromo 3-methyl hexane in presence of aqueous NaOH in when it undergoes an SN1 reaction. Okay, so what would be getting? Will be getting a mixture of enantiomers or structural isomers or mixture of diastereomers. So first we will write the structure, okay? Let's move to the next page and write the structure of 3-bromo 3-methyl hexane. 3-bromo 3-methyl hexane. So 1, 2, 3, 4, 5, 6. Write down in your notebook, okay? Write the structure of 3-bromo 1, 2, 3. Okay? So it is like 3-bromo. The third carbon has methyl group, 3-methyl hexane. So 3-bromo, 1, 2, 3, 4, 5, 6. 3-bromo, 3-methyl hexane. Okay. So it undergoes SN1 reaction. It undergoes SN1 reaction in presence of aqueous NaOH. It goes SN1 reaction. Now, what would be the product? What would be the product form? Like when you're doing SN1 reaction, know that it will be replaced with, okay, it will be replaced with OH. It will be replaced with OH. So, and here SN1 will have retention configuration or inversion configuration. Retention or inversion. What configuration does the SN1 reaction will have? Retention configuration or inversion configuration? What type of configuration will it have? SN1 will have the retention configuration. Yes, it will have, like, see over here, I have written the BR is replaced with OH and the bond is like wedge with bond. Okay. And will it have an enantiomer? Will it have enantiomer? So when you put it in the on the mirror image, okay, so you are getting enantiomer. So mixture of enantiomers are formed. Mixture of enantiomers are formed. So therefore, when you take option like R, you'll be getting mixture of enantiomer. So R is going to be like 3. And when you take the fourth compound, okay, when you take the fourth compound, when you put aqueous NaOH, now what would be the product you'll be getting? Like, you'll be getting one OH, yes, over here with the same configuration, and the other one would be the mixture, right? So you'll be getting like OH will be in the bond and you'll be getting an Me, okay? And again, you'll be getting MEH. So here you can see that this configuration is remaining same, only the second one, okay? This one, it is different. It is different, okay? So therefore, now tell me, like, whether they are enantiomers or diastereomers. Whether they are enantiomers or diastereomers, this is going to remain the same. Only one gets differs. Okay, only one configuration on the chiral carbon gets differs. So therefore, they are enantiomers or diastereomers. So what are enantiomers? The complete, like in a mixture, if the one is like R, or if it is like having plus, the complete should be like minus. So that is like R and R. Okay, if you have like two chiral carbons and if you have like RR, and the for enantiomers both should be like SS. Okay, then only it is said to be as enantiomer. For instance, if I'm taking this as R and this is S, so here it is remaining R only. This one is getting inverted to S is getting inverted to R. This one, like in the first chiral carbon, it is going to remain same. So if it is like RS and the other one is RR, so here you can see that S is have been converted to R, but this R is remaining as it is. So therefore, this case is said to be as diastereomer. Diastereomer. So how to remember this, ma'am, easily? Okay, I'll tell you. Yes. So now you just match this one with S with 1. Okay, so this is how you have to solve the question. Now I'll tell you like how to find out the enantiomer and diastereomer. Okay, so if you have like two isomers, it has only one chiral carbon. It has only one chiral carbon. Okay, so number of chiral center is 1. 1. And if the first isomer has R configuration and the second also has R configuration, then they are said to be as identical isomer or homomers. They are homomers or identical isomers. Okay. If you have like only one chiral carbon and if it is like R and the other one is S, they are said to be as enantiomers. Okay. Or if it is like S and R, it is enantiomer. So if they are both are same, it is identical. Okay. If one is R, the other one is S. If one is S, the other one is R. Just opposite. Then they are said to be as enantiomer. This is for one chiral carbon. Okay. So clear with this, everyone? Clear? Now I'll just go with the two chiral carbons. So if you have like two chiral carbons, if the configuration is RR and third it is like RR, then they are said to be as what? Identical. Okay, they are identical isomers. They are identical isomer. And now again. So when it is like SS and here too it is like SS, these are identical isomers. Identical isomers. Now here, if you have like RR, okay, totally the things converted, like there is inversion on both the things, then it is said to be as enantiomer. Enantiomer. Or if it is like SSRR or if it is like R, here R should be and S should be converted to R. So you can see that the configuration is completely inverted. So therefore, these cases are enantiomer. Okay. Now if I have like RR, and here if I have like R, the one same, the other one is different. Okay. Or if I have like S, and here I have like RS. So here you can see that like one is same, the other one is different. Okay. If any one of the thing is same, if both are different, it is enantiomer. If any one is same, then they are said to be as diastereomer. This is also applicable for all if you have like three chiral centers. Okay. So this is how you have to find out like whether they are enantiomers or diastereomers or homomers. Okay. So clear with this, everyone? Clear with this part, everyone? Clear with this? Any doubts? Okay, fine. Okay, so now I'll give you like a small thing to practice. Okay, now you find out whether they are enantiomers or diastereomers. Okay, so I have like a hydrogen over here, OH. Okay, and here I have again a hydrogen and OH. Okay, so like this, I have a thing. This is like one isomer. The other isomer is HOH, HOH. Okay, so now tell me like whether they are enantiomers or diastereomers. 1 and 2 are enantiomers or diastereomers. Just put it in the chat box whether they are enantiomers or diastereomers. What you have to look into the configuration. So here, see the configuration of hydrogen is having the wedge bond. Here too, hydrogen is having the wedge bond. So both will have the same configuration. Yes, the configuration is going to be same. And here hydrogen is having a wedge bond, and here hydrogen is having a dash bond. So therefore, they will have a different configuration. So if one has the different configuration, they are enantiomer or diastereomer. They are enantiomer or diastereomer. Enantiomers or diastereomers. Like one configuration is different means enantiomer or diastereomer. Just look over here. If one is same, yes, if one is same, the other one is different, they are diastereomers. So what should be the answer? If they are diastereomers. So one is same, the other chiral carbon configuration is different. So therefore they are diastereomer. Now for instance, okay, I'm going to change the configuration. Okay. So here what I'm going to do is like I have hydrogen in wedge bond, OH in dash bond. Now tell me like what type of isomer it is. Tell me like what type of isomer it is. What type of isomer it is? See the configuration of both the chiral carbons, whether they are same or different. So here I have like hydrogen in wedge bond, So therefore they are same. Yes, here I have like hydrogen in wedge bond. So therefore they are also same. So if both are same, then they are said to be as what? They are said to be as homomers or identical isomers. Both are same. Okay. If both are same, they are homomers. If one is different, then they are diastereomers, or if one is same, they are diastereomers. For instance, now I have hydrogen in dash bond. Okay. And here too, I have the hydrogen in dash bond. OH in wedge bond. Okay. Now tell me, like, what type of isomers they are? Like, both are same or different? Both are same or different. Here you can see that hydrogen in wedge bond. Here hydrogen is in dash bond. So therefore they are different. Different. Here you have like hydrogen in wedge bond, hydrogen in dash bond. So therefore they are different. Okay. If both are different, then what type of isomers they are? If both are different, they are enantiomers. Enantiomers. Okay. So remember this. If all identical, then they are said to be as homomers. Okay. If all carbons are different, if all are different, they are enantiomers. Okay. If you have like one same, and all others are different, or the inverse, okay, or one different, all others are same, okay. So in this case, these are said to be as what? Diastereomers. Got it now, everyone? Got it? Clear with this question? Any doubts with this question? Like, so this is how you have to find out whether they are homomers, enantiomers, or diastereomers. So this is very important. Okay, because I spent so much time for this part. Clear this, everyone? Any doubts? Okay, fine. So moving to the next question. The next question is, here you have like ClCl. Okay, it gives Cl free radical, whose delta H naught, change in enthalpy, is 58 kilocalories per mole. And for CH3Cl, it will form its methyl free radical and chlorine free radical, and its delta H value is given. HCl, its free radical and delta H value is given. For the following reaction, CH4 plus Cl2 gives CH3Cl plus HCl. What would be the correct statement? The initiation step is exothermic with delta H naught is equal to minus 58 kilocalories per mole. Propagation steps involves methyl free radical formation is exothermic with delta H naught of minus 2 kilocalories per mole. Propagation step inverse CH3Cl formation is endothermic with a delta H naught of 27 kilocalories per mole. The reaction is exothermic with delta H naught of minus 25 kilocalories per mole. Okay, so this is the question. Okay, so we know that it follows a free radical mechanism, hence it will have like the initiation step, propagation step, and termination step. Yes. So now moving with the question, CH4 plus Cl2 gives CH3Cl plus HCl. So what is the first step? The first step is like the initiation step. What happens in the initiation step? Free radical will be formed. Okay. So here when ClCl, it undergoes homolysis in presence of a light to form 2 times of chlorine free radical. Okay, chlorine free radical. So what would be the delta H naught? For the formation of 2 molecules of chlorine free radical. Okay, so it requires energy. To break the bond. So therefore, the delta H naught will be positive or negative. That is whether the reaction is going to be endothermic or exothermic.
Endothermic.
The first step, it needs energy. Yes, it should be endothermic, but here what they have given, the initiation step is exothermic they have given, so which is like incorrect. It is incorrect. Now moving to the next one, propagation step involving formation of CH3 is exothermic they have given. Okay. Now what happens in this free radical formation in propagation step? CH3 hydrogen will be there, like methane. I have taken methane. So CH3 hydrogen I have written. So here too, for the formation of free radical, delta H not should be like endothermic. Here too, what happens? To break the bond, you need energy. So therefore, this is also not exothermic. It should be like endothermic reaction. Endothermic reaction. Propagation step involving CH3Cl is exothermic. Sorry, it's endothermic with the delta H naught of 27 kilocalories per mole. Okay. So now the propagation step involving CH3Cl. Okay, formation of CH3Cl. So for formation of CH3Cl, what do you want? You want a methyl free radical and chlorine free radical. And here the bond is formed. So when the bond is formed, what would be the reaction? Whether it will be exothermic or endothermic. For bond breaking, it is endo. So therefore, for yes, it should be like exothermic. But here they have given as endothermic, which is going to be wrong. So the reaction is exothermic with delta H naught of minus 25 kilocalories per mole. Okay, so the whole reaction is exothermic or not. This is what we have to find out. So enthalpy of the reaction is delta H naught is equal to delta H1 naught plus delta H2 naught plus delta H3 naught. Okay. So delta H1 naught is like 58 kilocalories per mole. Okay. So it is 58 kilocalories per mole. Now, what is like delta H2 naught? Delta H2 naught is the propagation step involving formation of CH3 dot. Okay, CH3 dot. So, what you will be getting over here, you will be getting like 85 kilocalories per mole. Okay, 85 kilocalories per mole. Okay. And also we have studied that this one is like exothermic or endothermic. So this is like endothermic, yes, endothermic reaction. So it will be like plus 85. Yes. And then it comes the formation of the third one is involving the formation of CH3 dot plus Cl dot. Okay, formation of CH3 dot and Cl dot. So for the formation of CH3 dot plus Cl dot, I should inverse the reaction, right? I should inverse. So if I inverse, then you have to inverse the sign of this one too. So it will be like minus 85. Minus 85. Okay. And the formation of CH3Cl we have done. The formation of HCl, right? So HCl on breaking, it gives like 103. Breaking, it gives like 103. So for the formation, it should be like minus 103. Minus 103. So minus 103. Okay. So what value will be getting? 58. So you'll be getting like some 45 minus 45. So the reaction is like exothermic. Okay, you have got a negative sign. So the reaction is like exothermic, and the value over here is like somewhat different, right? They have given it as like minus 25 kilocalories per mole, but we got like minus 45 kilocalories. Okay, so Okay, so we have to write do the CH4 over here. I have done a mistake. Like delta H2 should be the CH4, right? We have done it. I have written this value for CH3Cl. So for CH4, it needs like CH4, it forms CH3 radical and H dot radical. H dot radical. So here you have to like for 2 Cl dot, you are getting 58. And here it is 1 Cl dot is moving out and you have the remaining CH3 dot. And here too you have like Cl dot moving out and here you have got the H dot radical. So you have to minus it for 1. And then you have to like add these together, you will be getting for CH4. Okay, have you got my point? There is no delta H naught given for CH4. No delta H naught given for CH4. So you have to combine like CH3 dot and H dot. You have to combine like CH3 dot and H dot. So for it, the value is like 105 kilocalories per mole. Okay, so which is missing in the question. Which is missing in the question. So if you substitute over here, then you'll be getting like 25 as the answer. So the reaction is exothermic with delta H naught is equal to minus 25 kilocalories per mole. Is the got this question, everyone? Yes, so this data is missing in the question. If you like substitute, you'll get the answer. Clear? Yes. So moving to the next question. Now we are going to apply the thing what we have studied in the first question over here. Okay, so which one of the following option represents identical molecules? So what is like for identical molecules, what we have to do, we have to find out the configuration. If both are same, it's going to be like identical. Yes, that is what identical molecule. But can you tell me the name of the projection which is given over here? What is the projection given over here? The Newman projection. We have a Newman projection. For doing the configuration, you have to convert it into Fisher projection. You have to convert it into Fisher projection first. Okay, so I'm going to convert each and everything into Fisher projection first. Only then we can do the configuration. Okay, so what is the first one given? The first given is, I'll write it again. So you have like CH3, CH3, C2H5, CH3, OH, CH3. This is what you have. Okay, so this is your first one. So now we want to convert it into the Fisher projection. Okay, you have to convert into the Fisher projection, or you can just write the name first. Okay, then we can write the Fisher projection. So what is the name? Like how many carbon it involves? It involves like 1, 2, 1, 2, 3, 1, 2, 3, 4, and 5. Okay, so this is the carbon chain over here. Okay, so I'll write like one chain. I'm taking this one. So 1, this is 1 is the carbon. So when I take this as 2, 3, and 4, I'll be getting. But when I consider the thing which is like below this one. Okay, so this is your first carbon, this is your second carbon, third carbon, fourth carbon, fifth carbon. So this is your parent. This is your parent. And here where you have the substituent, you have the substituent in the third carbon. Yes.
Third carbon.
And in the second carbon. Yes. So therefore, you just write the name. Okay. So where you have the substituent, you have the substituent methyl. Methyl is present on the rear carbon. I can say like 1, say is present over here at the rear carbon. Okay. So if this is your parent, CH3, this is first carbon, and this is your second carbon. You have like third carbon over here, and you have CH2, CH3. Now this is your parent. So where you have the substituent, you have it in the second, that is on the circle, you have one substituent. Yes, carbon, you have one substituent. And in the third carbon, how many substituents you have? Like 1, 2, CH3. And O is present on the second carbon. Now tell me the name. It is, can I write 2, third, 3, 3. It has like 3 methyl groups. 1 is attached to the second carbon, 2 is attached to the third carbon. So 2, 3, 3, trimethyl, pentane to all. Pentane to all. So this is the first one. Okay. Now to the second one. Okay, can I write the name for the second one and show the question? This is how you have to write the names. Okay. Yes. So now what is the name for the second one? So the first one I'll write is 2, 3, 3 trimethyl pentane to all. So what is the name for the second one? All these are like for the same isomer only. So pentane to all is going to remain same. Only the substituent is going to differ. Okay. So pentane to all is going to remain the same. Only the substituent will differ. So now can you tell me like which is the parent chain over here? So when I take this carbon, it is 1, 2, and it is like 3, 4, and 5. You have like 2 carbons. So this is your parent. Okay. So in the second one, I have like alcohol, I have methyl group. And so therefore, what would be the name? You have like third one, you have methyl group. And so therefore, what would be the name? Second one, you have a methyl group. Yes. And this is your third carbon. So third carbon, you have okay, I have missed this carbon. I have missed carbon. See, I have like 1 carbon in this part. This is also a carbon, right? This is also a carbon. And then you have, if I consider like taking this carbon over here, and it will be like 1, 2, 3, 4, 5, and 6. 6. Okay. So therefore, it is not going to be like pentane to all. Now just write the name. Okay, write the name. So you are going to just write the names for everything given over here. And the one which has both the names is same. Okay, that is going to be the identical isomer. It is going to be the identical isomer. Okay, so you are going to write the names for everything given, and you have to like find out the name which is matching. Like for both, it will be like same name. That will be the identical isomer. So this is one. You'll be writing the name to find out. Else, what you can do is like you can write you can convert it into the Fisher projection. Okay, so this is like finding out by writing the names. Okay, if you write the IUPAC names, the one which has similar name will be the answer. Okay, they are homomorphs because the name is similar. So that we can say that they are identical. Else, what you can do is like you can convert it into the Fisher projection. Then how will you write the Fisher projection formula? How will you write the Fisher projection formula? From Newman projection, you have like CH3, you have like CH3. Okay. So first you have to find out like how many chiral carbons you have. Like how many chiral centers you have? So this one is like, I can say this center carbon, okay, it is chiral, it is not chiral because you have like similar groups, CH3, CH3 over here. And here too you have like OH, CH3 attached. And here too you have like CH3 attached. You have like CH attached. So can you write the Fisher projection for them? Because here you can see that each and every family groups is a chiral. I'll show you. Right? Carbon in the middle. You have a CH3. You have another CH3. And here you have like H5. So you have like two same groups. So therefore, this carbon is a chiral. When you take the carbon which is surrounding, it is the carbon which is present at the back. Or it is CH3, CH5, and here I have like OH, CH3, CH3. Okay. Can I write the Fisher projection for this? No, because here you can see that the carbon are carbon. Yes, can't write the Fisher projection. So only we have to solve it by writing the names. Okay. So if you find like difficult to find out the carbon chain, what you have to do is you can convert this into the Sawhorse projection, and then you can just easily find out the name. Okay, if you convert like this, it will be like easy for you. So here 1, 2, 3, 4, 5. Now you can name it easily. It is 2 methyl. 3 you have like 2 methyl. So 2, 3, 3 trimethyl pentane 2. Okay. Same way we'll write the Sawhorse for the second compound also, because you have like only one option to do it by writing the IUPAC nomenclature. Fisher will not over here because we have like both the carbons chiral. All the carbons present over here is symmetrical. So therefore you can't do the configuration to find out the identical homomers. Okay. So this is for the first one. For the second one, again I'm writing the compound. So we'll write the Sawhorse. It will be easy to find out the name. Okay. So what is the second compound is? You have like C2H5 hydrogen. Here you have CH3, CH3OH. And here you have like hydrogen, CH3. Now what you have to do, you have to write it in the Sawhorse. So how will you write the Sawhorse? Consider like this carbon which is the center. Okay. And the carbon at the back is the circle. So just write the carbon at the back. What you have on the circle is hydrogen, hydrogen, CH3. So write it over here, hydrogen, hydrogen, CH3. And what you have in the dot carbon, you have like one hydrogen, you have C2H5, and here you have like another carbon having CH3, CH3OH. Okay. We like find out the longest chain. Find out the longest chain over here. Like you have 1, 2, 3, 4, 5. I have like 5. Yes, I have 5. And 3, 4, 5. Now tell me the name of this one. You have like ethyl, 3 ethyl. And you have like in the second one, you have a methyl group. So 2 methyl, pentane, 2 all. Pentane, 2 all. So by writing it in the Sawhorse, we'll be finding it easy to write the names. Okay. Now moving with the third question. Moving with the third question. So what is, so I'll just here you have like CH3, CH3OH. I'll write CH3, CH3OH. Okay, you to write it in your notebook. Here you have like C2H5, H C2H5, C2H5, C2H5. Okay, so now find out the longest chain. Which one would be the longest chain over here? Find out the longest chain. You have like 2, 3, 4, 5. Okay. So that would be the, so it is like 1, 2, 3, 4, and 5. Now when you again it's to metal, pentane to what? This is also like 3 metal, 2 metal, pentane to what? Okay. So now can I say that are critical isomer because the name is same. The name is okay. When you take the compound, what would be the name? What would be the name? Okay, for the fourth compound. For the fourth. Okay, so is it clear to everyone? Is it clear? So you can see that this has the same names. Okay, so Q and R. So Q and R has the same names. So option C is going to be the right answer. Got it? So if the given, either you can convert it into the Fisher projection if you have the chiral and then find out RS. Else just write, convert it into Sawhorse, find out the name, and the one which has like if both has the same name, they are going to be the identical isomers. Got it?
बावड़े
Yes.
कुत्ते पे तेरे
Coming to
लैपटॉप
the
का मार दूं पहन लग जा एक मार मेरे पे देख रहा है तेरा अच्छा हो तो मना कर दे फिर पहन दे कुत्ता सा नहीं सुअर पहन ले पकड़ी पैसे मुझसे मुझसे नहीं
kindly mute. So the next question is D-erythrose and its
मैम
isomers are listed as yes.
मैम समझ नहीं आ रहा मैम, थोड़ा अंडरस्टैंडिंग करने की कोशिश कर रहा हूँ पर समझ नहीं आ रहा, थोड़ा हिंदी में बोल लेंगे आप?
No, so the students are from all the states, right? So I can't do it in Hindi. Like, see, if you have like, if you are want to like repeat it again, see, this one
No.
is live streamed in the YouTube. Like after the class also, you can again you can watch the video so that you can get it. Yes,
ओके मैम.
fine. So the next question is D-erythrose and its isomers are listed as PQ, R, and S in column 1. Choose the correct relationship of PQ, R, and S with D-erythrose from column 2. Okay, so here to like, you have to do it whether they are like enantiomers, diastereomers, or identical isomer. Okay, so what you can do here, like find out whether it has a chiral center, Yes. Like when I take 1, 2, 3, 4, I have hydrogen over here. So therefore it is a chiral center. And okay, so it is a chiral center. 1, 2, 3, 4. And here too it is 1, 2, 3, 4, which is different. It is a chiral center. So I have like 2 chiral centers. I can like make a Fisher projection. So if I write the Fisher projection, yes. So what I have over here on the plane is like CHO. And right over here, yes, CHO. And here I have a chiral. And this one is also a chiral center. And next I have like CH2OH. CH2OH. Yes. And just like you have to write here you have like hydrogen OH, okay, and here too you have like hydrogen OH, and here you can see that this hydrogen is present like below the plane. It is present below the plane, and OH is like on the plane. OH is like on the plane, and here it is hydrogen is on the plane and OH is below the OH is below the plane. So now what would be the configuration? So I have like hydrogen, yes, and you have like OH. OH, and you can see that this bond is tilted. It is tilted. So when you like bring it to the same side, what happens like now the thing's going to be, it will be having a wedge bond, it will be having a dash bond. So I can say that it will have the same thing like HOH. HOH. Now you can see that the erythros and this one. Okay, so both are same. Both are same. So therefore they are identical. They are identical. Now moving to Q. Moving to Q. Okay, so Q has, again you write the Fisher thing. So you have like CHO, CH2OH. Here OH, like you can see that they are present on the same side. So no need to like tilt it. Okay, you just write as it is. So if you write like this is below the plane, this should be like above the plane. So below the plane, you have like OH and hydrogen over here. Here below the plane, you have like H. Okay, here you have H and OH over here. Okay, now is it same as of the first the erythros? No, it is not same. Okay, so either it should be an enantiomer or it should be a diastereomer. That will do it later. Now first I'll write the Fisher projection and now again this is like CHO. You have like CH2OH. Now you want to fill this one or write it as it is. Like they are just opposite to each other. Opposite to each other. Now inverse it. You have a wedge bond over here and you have a dash bond over here. Okay. So you have like below above. So below the plane you have like hydrogen. So OH will come this way. And here you have like OH and hydrogen will come this way. Okay. So this is like C. And now moving to the last one, Fisher projection. CHO, CH2OH. Okay, now you have it on the same side. So do you want to tilt it? No, no need of tilting. Just write like below and above. So below you have like OH, hydrogen, and here below you have like OH, hydrogen. Okay, fine. So now moving to the comparison. Now, D-erythros, the first one, you can see that hydrogen OH are at the same. Like if hydrogen is present on the left, OH is present on the right. So therefore, going to be like identical. Now, moving to Q and D. Okay, Q and D. Can I say that they are mirror image of each other? This is erythro. So when you compare this Q and D, can you say that they are mirror image of each other? Are they mirror image of each other? Are they mirror image of here? No. If they not mirror images, then the set to be is what? Diastereomer. Diastereomer. Now, or else you can see like one configuration is going to remain same. So you can see like H. Yes, it is remain same. But the second, the first chiral carbon configuration is different. Okay, it's different. So we know that like the same they are diastereomer. Like compare the they are anxious diastereomers or enantiomer. Just compare and tell me. R and D erythro. Compare and tell me. Like see the configuration or look into like they whether they form the mirror image. They are enantiomers or diastereomers. So see over here, you have like hydrogen on the left, OH on the right. Here you have like hydrogen on the left, OH on the right. Yes. And the second one is OH on the left side, but here you have OH on the right side. You have OH on the right side. So one configuration is same, the other one is different. So therefore, tell me like whether they are enantiomers or diastereomers. Whether they are enantiomers or diastereomers.
Diastereomer.
Very good. So it is a diastereomer. Diastereomer. Now same way like compare S. Compare S. So here you have like OH hydrogen, which is different with the D erythros. And here too you have like OH hydrogen, which is different with D erythros. So both are different. If both are different, then they are, or you can see that they are just mirror images of each other. So they are enantiomers or diastereomers. Yes, they are enantiomers. Now, like match this one and find out which is your correct answer. Which is the correct answer? This is like identical. It is diastereomer. Third is also diastereomer, and fourth is enantiomer.
Option
C. Got this question, everyone? How to find out like enantiomer, diastereomer? Got this question?
Ma'am, will there be an image of the de-erythroid will be given?
What you're asking? De-erythroid. Yes, it is given in the question. It is given in the question. Okay, fine. Now, the next question is, isomers of hexane based on their branching can be divided into three distinct classes, which is shown. Now, what you have to find out is the correct order of their boiling point. What is the correct order of boiling point? Is the question. What is the correct order of boiling point? So 1, 2, 3 is given. Like what would be the order? What happens when the branching increases?
The boiling point is because of the surface area decrease.
Yes. Boiling point will decrease because of the less van der Waals force of friction. So now like which has like more branching, or right, the boiling point will be minimum. Or I can say that the one which has no branching at all, the boiling point will be maximum. So which option will be right? Here I have like no branching at all. Okay, so 3 will have the highest boiling point. So look at the option B and D. And now when you compare like 1 and 2, okay, so where the branching is less, boiling point will be more. So here the branching is less. Here the branching is more. Okay, you have like 2 branching. Over here you have like only 1 branching. So therefore option B is going to be the correct answer. Yes. And next question is, the maximum number of possible isomers may be formed from monobromination of 1-methyl cyclohexamine using Br2 and UV. Yesterday I have told you to find out how to find out the number of products, like monobromination or monochlorination. I have taught you. Okay. So now we are just going to write the compound. Okay, so what is the compound over here is like 1-methyl cyclohexamine. So this is cyclic compound. I have 1 in over here, and the first has methyl group. So this is like 1-methyl cyclohexamine. Okay, so this on presence of UV light, what happens now? It will form the radical. It will form the radical. And I have told you to find out the maximum number of possible isomers, you have to look it for the different environment of hydrogen. Okay, so how many different environment hydrogen you have? Those amount of product you will be getting. Okay, so can I say like this one? You have one different environment because CH3 is attached to carbon, and here there is no CH3 at all. So this is like one different environment. You have like one different environment. And here there is no hydrogen at all. So in the second this carbon, so no bromination will take place. Now moving to this one. So this one is like CH2 attached to another CH2 and the carbon. Okay, another CH2 and carbon. So making this as B. Now here I have like one more CH2. This CH2 is attached to CH2 and CH2. Okay, so this is of different environment. It is not A or B. So here this B is attached to carbon and CH2, which is B. C, this carbon is attached to both CH2, CH2, which is of different environment. So C. So C. Now move to this one, CH. Okay. So I mark it like 1, 2, 3, 4. So this is first carbon, second, 3, 4, 5. Now when you make it 5, making 5. Okay. So whether the thing is like same or different, whether it is like same environment or different environment. You have CH2, CH carbon over here, and you have like CH2, here it is CH carbon. So which is different? CH2, CH2 carbon, CH2, CH carbon is different. So this is of environment D. And here you have like CH2, CH2, CH, which is also like different. So E. And here will be like, so all the hydrogens which is attached are totally different from one another. So bromination takes place at each and every hydrogen different environment. So how many environment you have? Like 1, 2, 3, 4, 5, and 6. So your answer is going to be like 6. Got this question, everyone? Yes, you have to find out like whether the environment is same or different. If the environment surrounding is same, then you'll get like only one product or both. Here, like everything is different, so you'll be getting like 6 different brominations. Got it? Clear this question? Yes. So now I'll just give you like one more example. So now tell me, like when you do bromination over here, how many products you'll be getting? What will be the max cost products when you do bromination for this compound? So what you have to check? You have to check like different carbon, different hydrogen environment. So I'll like write all the carbon over here. So therefore it will be easy for us to identify. Okay. So now tell me, like I'm taking the CH3 is attached to CH. Attached to CH. This CH3 is also attached to CH. So are both CH3 are of same environment or different environment? Both CH3 are of same environment or different environment?
Same.
Yes, same. So I can both are E. Okay. Now moving to this carbon, it has CH, CH3, CH2, which is different. Which is different of E. Okay, different from E. Now the H2, this one does not belong to B or A. Does not belong to B or A. So therefore it is going to be like C. Because you have like both CH, CH attached. Okay. Look over there. Look over there. It is CH3, CH, which is different. This two has CH3, CH. Okay. Here too you have like CH3CH. So it is of like same environment or different environment?
Same.
Yes, it is going to be A. Now when I take the CH, it is attached to CH2, CH2, but the CH has CH3, CH2, which is different. So C, we have done like A, B, C, B. When I take the CH2, it is CH, CH3. Here it is like CH, CH. So it is different E, and here it will be different S. So how many like you can get like 1 A, B, C, D, E, and so you can get 6 monochlorinated or 6 monobrominated. Got it? So this is how you have to find out the maximum number of possible isomers. Okay, which may be got it. Then you have like 6 isomers. Now, question they asked for the including stereo isomers. So you have to include the stereo isomer. You got like 6 isomers. For each isomer, if there is like any stereo isomer, you have to write the stereo isomer. You have to add the stereo isomer also. Okay. So now we will get the product and therefore say whether it has a stereo isomer or not. So when it has some chiral second, it will have the stereo isomer. Okay. So now I'll write the product. So in environment A, one hydrogen will be replaced with bromine. So you'll be getting like CH2Br. The remaining you're going to take. So this is like one product. Okay. Now this Br is attached to a chiral center or a non-chiral center. Br is attached to chiral center or non-chiral center.
Non-chiral center.
Non-chiral center. So will it have a stereoisomer? No. So no stereoisomer. No stereoisomer for the first. Now with the second one, in B, what you have to do, you have to replace one hydrogen with B. So I'm writing this H3. Now you are going to replace it with the Br. You have to replace it with Br. Okay. And you have a double bond, and you have a double bond over here. Okay, double bond over here. Okay, so now what happens over here is like this one is attached to a stereo center or no?
Stereo center.
So how many it will form a stereoisomer. Okay, so whether it will be like it will form an enantiomer. Okay, so therefore here you will be having like 2. So if I make like 1, here itself you have like 2, 3 isomers. Okay, and to this part. Okay, so from here itself we can say whether it have a C isomer or not. So when I remove like hydrogen and replace with B, whether it's a chiral or a chiral carbon. Whether it is a chiral carbon or a chiral carbon, when you replace it with Br. So one hydrogen I'm replacing it with Br. Okay, so here Br will be over here. So now here this is also carbon. So I can write like 4 and 5. Okay, again to replace like 1 here, get a chiral center. Okay, so 6 and 7. And here too, you can get like 8 and 9. Okay, then take this one. Okay, so here it is like Br over here, and you have a double bond, and you have a CH3, and you have a CH3 over here. Okay, so now like look over this one. Look over this one.
Chiral.
So therefore you have like 11, 10, 11. Okay, so 10, 11. So you have like 10, 11. So how many isomers we have got by like doing this? You have like 1 over here. So 2, 3. Okay, 4, 5, 6, 7, and 8, 9, 10, 11, 12, 13. So the total number of isomers will be equal to 13. So this is how you have to find out, like whether it has a chiral center, it will form like stereoisomer. 2 isomers will be there. Then here to alone, you don't have the stereoisomer. Okay, here alone you don't have the stereoisomers. So all the others you have the stereoisomers. Got it? Okay, so next question is total number of isomers considering both structural and stereoisomer of cyclic ether with the molecular formula C4H8O. You have the formula as C4H8O. You have to find out it is a cyclic ether. You have to find both structural and stereoisomer. Okay, so it is a cyclic ether. You have like C4H8O. C4H8O. So C4 oxygen at the middle because it is a ether. So this is like C4H8O. Okay. So this is like one you can write. And you can write like making 3 carbons and 1 carbon at the substituent. You can write, yes. So this one is attached like which is adjacent. This is a chiral. It is a chiral. And when you write over here, I can make the methyl group over here too. So therefore, oxygen, I can make it here. Okay. If I make it here, both are same. Both is going to be same. And when I make a 3-membered ring, the side chain will be like 2. Yes, 2. And you can make it like 2 CH3 on the same carbon, or you can make it like 1 CH3 over here, 1 CH3 over here. So I have got like 6. Now you have to find out like whether it has a chiral center. Here there is no chiral center, so you'll be having only 1. And here how many chiral center you have? Like 1 chiral center, you'll be having like 2 isomers. Okay, you'll be having like 2 isomers. And here too, you have like 1 chiral center, 1 chiral carbon over here. Yes, so therefore you'll be having like 2. So 2, 4, 5 you got. And here I have like 1 chiral center. Okay, so I'll have like 2. So 2, 4, 5, 6, 6, 7. Okay, here there is like no chiral center. So 8. And here too you have like chiral centers. So 2, 4, 6, 8, 10. Okay, so what is the total number of isomers possible? The total number of isomers possible is like, okay, here there is no chiral center because the thing attached is same. Look over here, this one, you have like CH3, carbon, CH2O, CH2. So no chiral center. So I have like 1 isomer. But here I have like 2 chiral centers. So therefore I'll be having 2 isomers for this one, 2 isomers for this one. So 4. So 4, 5, 6, 7, 8, 9, 10. Okay, so you'll get the number of isomers. Okay, you'll be getting the number of isomers. So here you'll be getting like 3 isomers because you have 2 chiral centers. It could be like RR, RS, and S. Okay, so therefore these are the 3 isomers. So therefore total number of isomers will be equal to. Okay, got it everyone? Got this question? Yes, sir. Moving to the next question. Okay, so for the given compound, the total number of optically active stereoisomer is. What is the total number of optically active stereoisomer? What is the total number of optically active stereoisomer? So find out the chiral center, you'll be getting the answer. How many chiral centers you have? How many chiral centers you have? So I have like 1 OH over here. Yes. And here you have this carbon, okay, carbon, Okay, so you have to write the optically active stereoisomer. Okay, so for each and every carbon, okay, if it has some chiral center, then you can write the stereoisomer for it. Okay, so how many chiral centers you have? Like you have one chiral center over here, and this is your like. No, it is not a chiral center. Like while you're writing the cyclic compound, you should be very careful. See, you have like CH2, C, and the whole group attached. You have to see the whole group attached. It is going to be like same. So here there will be no chiral. There will be no chiral. Okay. Now, carbon. This carbon. It has like COH, CH2, COH, which is different, and this part is different. This part is different. So this is like chiral, and here too like this chiral center. It is like a chiral center. Okay. Now what about this OH? It is different. It is different. Okay, so you have like 4 different chiral centers. So 4 into 2, you'll be getting like 8 optically active. 8 optically active stereoisomer. Okay, so you'll be getting like 8 optically active stereoisomer, in which like one will be a mesoisomer. Like if I make this one as OH bond and this as OH bond, now this is going to be a mesoisomer. Okay, so one will go to remain as a mesoisomer. So therefore, I'll be getting like 7 optically active isomers. So this is how you have to find out the optical active isomer. Okay. So the next question is like, this will be a homework. The number of aromatic compound, you know that what the rules for aromatic compound, it should be like planar, conjugated, and it should follow Huckel's rule. Okay. 4n plus 2, 5 electrons. So using this, you just do the number of aromatic compound. Yes, this will be your homework. Yes, so with this, I'll stop like today's class, and tomorrow you'll be having a mock test paper. Yes, so do the paper well, and we'll be solving the paper in class. Okay, in the next class, we'll be solving the paper. Yes, got it, everyone? So I'll share like today's PDF in the group. Okay, go through it again, like solve it and solve the questions what we have done it in the class, because they are like vital questions which were asked like previous years, were the questions which were asked by departments. So you can once again, and I have like some few extra questions which is left out. You can solve it, like you can take some and you can solve. Okay.